Hi, my name is Sachini Rajapaksa, and today I'll be presenting the article Flexion of the Elbow from Introductory Biomechanics from Cells to Organisms. This article endeavours to estimate the stresses in the forearm caused by holding a weight in place against the force of gravity. The background of the article primarily explores the anatomy of the forearm, identifying the key bones and muscles involved when holding up a weight. It denotes the key bones in the forearm as being the radius and the ulna. The bones in the forearm are mentioned in Lecture 1 of the VM portion of EL 516. It then considers the main characteristics of the four major muscles involved with holding up the aforementioned weight, these being the biceps, brachialis, brachioidalis, and extensor carpi radialis longus. It then estimates the origin and insertion points of those four key muscles to the forearm from anatomic drawings and utilises pre-existing data from prior studies to estimate the physiological cross-sectional area of the muscles. The force generated per unit PCSA of muscle is defined as F and is estimated to be 20 newtons per centimetre squared, which is again approximated from pre-existing studies. I'll then move on to discussing the methodology of the article now. So the forearm is then isolated from the rest of the body and modelled as being a singular beam in equilibrium, thus creating a free body diagram. Free body diagrams in two-dimensional cases was covered in slides 5 to 8, Lecture 3 of EL 516, and a very similar free body diagram of an arm holding a weight was covered in Assignment 1 of EL 516. So for these muscles now, the centroids were used to model the position of the resultant forces of the four key muscles in the forearm, and the weight was modelled as being a singular force acting on the wrist and hand region. And then the horizontal and vertical reaction forces were defined at the elbow. Determining centroids was introduced on Slide 4, Lecture 11 of EL 516 and Lecture 2 of EL 614. An example showing how to determine this for different shapes was then explored on slides 7 to 9 of both lectures. As the total sum of the moments must be zero at equilibrium, this property was then used to obtain this equation over here, which essentially just displays that the sum of all the anti-clockwise moments from the tensile forces of the four muscles must be equal to the clockwise moment from gravity acting on the weight being held. The conditions of equilibrium and rotational equilibrium were covered in Slide 4, Lecture 3 of EL 516. So, submitting in the assumed values for force generated per unit PCSA of muscle, and the length from the weight to the centre of rotation of the elbow allows the weight to be determined as being 120.1 newtons. The joint reaction forces in the y direction were then determined from the summation of all the vertical forces acting on the elbow's centre of rotation, and was found to be 377.6 newtons. The same approach was then used to determine that the joint reaction forces in the x direction was 304.3 newtons. Determining the scalar components of force was covered in Slide 4, Lecture 2 of Module EL 516. To allow analysis of the internal forces and moments, the forearm was then modelled as being four separate cantilever beams by isolating the segments at the location of the centroids of the four aforementioned muscles. So the bending moment is the torque applied to each side of the beam if it was cut at the point of the centroid of the muscles where the forces are acting on the beam. It was determined by taking moments about the imagined cuts, using the equation m equals px at rotational equilibrium. Determining the bending moment was covered on slides 4 to 8, Lecture 3 of Module EL 614. Then the areal moment of inertia for the bone cross-section about the z-axis was found using the following equation, which finds the integral of the distance from the neutral axis of the bone to the surface, y, with regards to cross-sectional area, a. Finding the position of the neutral axis was covered on Slide 9, Lecture 4 of EL 614, and then determining the second moment of area was covered on slides 10 to 11. The axial stress due to the bending moment and compressive internal force was then found by substituting the known values into the below equation. Determining the axial stress was covered in slides 3 to 9, Lecture 1 of Module EL 614. The forearm was then modelled as a singular hollow beam to represent the radius bone. This was done using pre-existing data from existing studies to approximate the length and diameter of the radius bone. The hollow structure of bones was mentioned in Lecture 1 of the VM portion of EL 516. The polar moment of area was then determined by inputting the approximated values into the following formula to compute that the moment of inertia was to be 0.177 centimetres to the fourth, and the area was 1.15 centimetres squared. Determining the polar second moment of area was covered on Slide 8, Lecture 5 of EL 614. The forearm was then modelled as being a truss beam consisting of two hollow beams to represent the radius and the ulna. Given both the radius and ulna carry a portion of the bending moment, it is understood that the total bending moment would be a summation of the bending moments in the radius and the ulna. Using this, the equation for axial stress in a hollow beam was adapted as shown below to determine the stress on both the radius and the ulna. With the understanding that the maximum stresses on each of the two bones are likely to be equal, the following equation is formulated. This is then simplified to the following equation, based on the assumptions that the diameters and areal moments of inertia are expected to be the same. Substituting in the approximated numerical values from before will give a maximum stress of 4,599 newtons per centimetre squared. So now I'm going to discuss the article. So the article explores different mathematical approaches to approximate the stresses in the forearm when holding a weight of 120 newtons. The methods used were all previously explored in the biomechanics and biomaterial modules and provided a deeper understanding of the practical real-life uses for the concepts that I have studied. This was then expanded by utilising techniques that we had previously covered to apply them to truss beams, which required combining the methodologies in a novel way I hadn't seen before. The article also placed emphasis on using different techniques to model the forearm, from the initial Euler-Bernoulli beam to then the hollowed cylindrical beam, before then modelling it as a truss beam. This provided greater insight into the ability to use mathematical approaches to model functions of the human body. The efficacy of this was demonstrated throughout as the calculated values for the stress on the beams became closer to the expected values from experimental data, thus further demonstrating the importance of accurate modelling. While this required a lot of assumptions to be made, this allowed for components of the forearm system to also be overlooked, such as the additional muscles involved and the additional tissue layers present. I believe this was done effectively and appropriately to allow for a more accurate result through the utilisation of assumptions with explicable justifications. This shows how relevant assumptions can be utilised to simplify the complexity of the problem to a task that is manageable at my current level of study. Thank you.